Hello friends, I welcome you in lecture number 7 on normal distribution. In this lecture we will do some examples on the normal approximation to the binomial distribution. In previous lecture we have discussed that if number of trials in a binomial distribution are large, then under certain conditions we can apply normal distribution to approximate binomial distribution. So as we have discussed, the normal approximation is good for approximating binomial distribution if n into p is greater than 5 as well as n into 1 minus p is greater than 5. Some authors consider this condition as n into p is greater than or equal to 10 and n into 1 minus p is greater than or equal to 10. So both are valid conditions. Either we can use this as well as this. Also we have discussed in the last lecture that while applying normal approximation to approximate binomial distribution, we have to take care of continuity correction. So as we have discussed that if capital X is a binomial random variable, then X is a discrete random variable, and if small x is the value of this discrete binomial random variable capital X, then probability that capital X equal to small x can be converted into this probability, which gives us the area under the normal curve between x minus 0.5 and x plus 0.5. So we will remember this continuity corrections. Probability that capital X equal to small x will be converted in this probability that x minus 0.5 is less than x plus 0.5. We have discussed how we are converting this probability of discrete random variable into probability of continuous random variable. So for that explanation you can watch lecture number 6 on normal distribution. Also we have seen that probability that capital X is less than or equal to x is converted in terms of probability that capital X is less than or equal to x plus 0.5, and probability that capital X is greater than or equal to x is nothing but probability that capital X is greater than or equal to x minus 0.5. So it is easy to remember these probabilities. If we have capital X is less than or equal to small x, then we will add 0.5 in this x value, and if capital X is greater than or equal to small x, then we will subtract 0.5 from x value. And if we have this type of less than x is less than suppose 3, so if we have this type of probability which says that capital X is less than 3 but capital X is not equal to 3, so we can convert this probability in terms of this probability, because capital X is a discrete random variable. Capital X is less than 3 is equivalent to probability that capital X is less than or equal to 2, and if we have this type of probability capital X is less than or equal to x, then it is converted into normal probability by adding 0.5 to this x value, as we have done here. Here capital X is less than or equal to x, so we add 0.5 to the value of x. So here we have 2 plus 0.5, that is probability that capital X is less than or equal to 2.5. So this is probability in terms of binomial random variable, and this is probability in terms of normal random variable. Similarly, if we have probability that capital X is bigger than 3, then because x is a discrete random variable, this is equivalent to probability that x is greater than or equal to 4. So that we can convert into normal random variable by subtracting 0.5 from this 4. So this is nothing but probability that x is greater than or equal to 4 minus 0.5, that is probability that capital X is greater than or equal to 3.5. So here we are using this probability that capital X is greater than or equal to X is nothing but probability that capital X is greater than or equal to X minus 0.5. So this probability is not in this form, but because capital X is a discrete random variable, we can write this as probability that capital X is greater than or equal to 4. These two are equivalent, both are equal. And once we have this type of probability, X is greater than or equal to small x, we have to subtract 0.5 from small x. So we subtract 0.5 from 4 and we obtain this probability, which is in terms of normal random variable. So we can remember these three things, and so that we can easily apply this concept of continuity correction while approximating binomial distribution using normal distribution. And whenever we have probability that capital X equal to small x, we will subtract 0.5 and we will add 0.5, and the corresponding probability for normal distribution will be probability that X minus 0.5 is less than capital X is less than small x plus 0.5. So with this in mind, we try to do some examples on approximation of binomial distribution by normal distribution. So we start with this example number 1. Suppose that 25% of all students at a large public university, this is written 2 times. Suppose that 25% of all students at a large public university receive financial aid. Let capital X be the number of students in a random sample of size 50 who receive financial aid. Find the probability that at most 10 students receive financial aid, and find the probability that between 5 and 15 inclusive of the selected students receive financial aid. So here capital X is given to be the number of students in a random sample of size 50 who receive financial aid. So we have given this sample of 50 students, and for each student there are only 2 possibilities: either particular student receive financial aid or that student does not receive financial aid. So there are only 2 possible outcomes for each student: either student receives financial aid or student does not receive financial aid. And it is given that 25% of all students at a large public university receive financial aid. So probability that student receives financial aid is 25%, that is 0.25. Now it is obvious that if one student receives financial aid, so that does not affect the receiving of financial aid of other students. So we can assume that trials are independent, and because there are 50 students in the sample, we can say that number of trials are finite. So we can observe that all the 4 conditions of binomial distribution are satisfied. So this is the example of binomial distribution. Now in first part we are asked to find the probability that at most 10 students receive financial aid. So at most 10 means either 10 or less than or equal to 10. So we have to find this probability that capital X is less than or equal to 10. And in the second part we have to find the probability that between 5 and 15 inclusive means we have to include 15 as well as 5. So we have to find this probability that between 5 and 15 of the selected students receive financial aid. Now if you go by using binomial distribution, here you have to calculate the probabilities starting from x equal to 0 up to x equal to 10. So we have to calculate 11 probabilities, and here also we have to calculate probability starting from x equal to 5 to x equal to 15. But we are not using that binomial distribution to find this probability. We will try to use normal distribution to approximate these two probabilities. For that we have to check two conditions. Here we have sample of size n equal to 50, and if we assume that student receives financial aid, if that event is considered as success, then it is given that probability of success is 0.25. So we find out n into p and n into 1 minus p, and we check whether both are greater than 5 or not. So we have to write systematically. Here capital X is the number of students who receive financial aid among n equal to 50 students. Now if the event that student receive financial aid is success, then it is given that probability of success is 25%, that is 0.25. And as we discussed, capital X is a binomial random variable with n equal to 50 and probability of success p equal to 0.25. Now we check whether it is possible to apply normal distribution. So for that we find out n into p. N is 50, p is 0.25, so it is 12.5, and n into 1 minus p is n is 50, 1 minus p is 0.25, so 50 times 0.75, which is 37.5. So you can see both are greater than 5, 12.5 and 37.5. So it is possible to approximate given binomial distribution using normal distribution, and with mu equal to, mu is the mean of normal distribution, or parameters of normal distributions are mu equal to n into p, which is 12.5, and standard deviation is square root of n into p into 1 minus p. So n is 50, p is 0.25, 1 minus 0.25, which is 0.75, and if we calculate this, square root is 3.06. So parameters of normal distribution are mu equal to 12.5 and sigma equal to 3.06. So the binomial distribution with parameters n into n comma p is approximated by the normal distribution with parameters 12.5 and sigma square, or sigma is 3.06, so sigma square is square of 3.06. So we will use this normal distribution with parameters mu equal to 12.5 and sigma equal to 3.06 to calculate probabilities of given binomial distribution. So the first probability required is probability that at most 10 students receive financial aid. So this event can be represented by capital X is less than or equal to 10. At most 10 means either 10 or less than or equal to 10. Now this X is a discrete random variable, so we have to convert this discrete probability in terms of continuous probability. So as we discussed, we have to apply continuity correction. So we know that if we have this type of discrete probability, then continuity correction is we have to add 0.5 to the X value. So here we add 0.5 to the value which is 10 here. So this is equal to probability that capital X is less than or equal to 10.5. And if you want to understand this, as we have discussed already in the last lecture, that because X is a discrete random variable, and we are approximating x with normal distribution. So suppose 10 is somewhere here. Suppose this is the value of capital X equal to 10, and we are asked to find the probability that capital X is at most 10. That is, we are interested in the area to the left of 10. That means we are interested in this area which is to the left of 10. But as we discussed, that probability that x equal to 10 is nothing but the area of rectangle with center as 10. So we have to include this rectangle for the probability that capital X equal to 10, and we know that this correction is 0.5, so this point is 10.5. So at most 10 means we have to go up to this right boundary of the rectangle, because this rectangle corresponds to the probability that capital X equal to 10. So to include this probability, we have to go up to right boundary of this rectangle corresponding to this probability that x equal to 10. So this is approximately equal to probability that capital X is less than or equal to 10 plus 0.5, which is 10.5. So this is nothing but area under the normal curve to the right of 10.5. Now this is capital X is normal random variable. So we have to standardize this normal random variable by subtracting mu and dividing by standard deviation. So this is equivalent to probability that x minus mu over sigma is less than or equal to 10.5 minus mu over sigma. Now this capital X minus mu over sigma is capital Z, standard normal random variable, and here we substitute values of mu and sigma. Mu is 12.5 and sigma is 3.06. So after simplifying this, we have probability that standard normal random variable is less than or equal to minus 0.65. Now this probability we can calculate using standard normal probability table. So we require probability that Z is less than or equal to minus 0.65. So we look for minus 0.6 in this table. So this row corresponds to minus 0.6. We are interested in this value of Z, minus 0.65. So that we can rewrite as minus 0.6 minus 0.05. So we have to go up to 0.05. So 0.05 is here. So we have to start from 0 up to 0.05. So minus 0.6, this corresponds to 0.00. This is for 0.01, 0.02, 0.03, 0.04, and this corresponds to 0.05. So minus 0.6 and this column corresponds to 0.05. So required value is 0.2578, which we have written here, 0.2578. So probability that at most 10 students receive financial aid is 0.2578. Second example, second part, probability that between 5 and 15 of the selected students receive financial aid. That means we have to find the probability that capital X lies between 5 and 15. So this we can convert into continuous form by subtracting 0.5 from 5 and adding 0.5 to 15. Okay, we are interested, for example, if we have capital X is less than or equal to 15, then we can write this as capital X is less than or equal to 15.5. If we have less than or equal to type probability, we add 0.5, and if we have this type of probability that capital X is greater than or equal to 5, then we subtract 0.5, that is, so here we have both the type of probabilities, less than or equal to as well as capital X is greater than or equal to 5. So here we add 0.5 and here we subtract 0.5. So this is approximately equal to, this is not exactly equal to, we are converting discrete probability in terms of continuous probability. So this we can rewrite as probability that 4.5 less than or equal to capital X less than or equal to 15.5. Now we standardize by subtracting mu and dividing by sigma. So this is equal to, now probability that 4.5 minus mu over sigma is less than or equal to X minus mu over sigma, which is less than or equal to 15.5 minus mu over sigma. And then we put values of mu and sigma. Mu is 12.5, sigma is 3.06, and after simplifying we obtain that this probability is equal to probability that minus 2.61 less than or equal to Z less than or equal to 0.98. Now as we know, this probability can be rewritten as probability that Z is less than or equal to 0.98 minus probability that Z is less than or equal to minus 2.61. So we look for these two values in the table, 0.98. So first we concentrate on 0.9. So this is the row corresponding to 0.9, and we have to go up to 0.8. We are interested in this value 0.98, that means 0.9 plus 0.08. So here we concentrate here. So we take intersection of these two and here up to this. So the required probability is 0.8365. .98. Just a minute, I have to check. Okay, so it is 0.98, so we have 0.8365. So instead of this, we have to write 0.8365 minus probability that Z is less than or equal to minus 2.61. So we have to concentrate on minus 2.61. Minus 2.6 is here, and we have to go up to 1. So minus 2.6 and 0.01. So it is 0.005. So we put here 0.005. And then we take the difference of these two, 0.8365 minus 0.0045. So the difference is 0.8320. So we write here 0.8320. So in this way we can approximate binomial probability distribution using normal distribution with certain conditions satisfied. Suppose we have to remember these two conditions: n into p is greater than 5, n into 1 minus p is greater than 5. Then we can apply normal distribution to calculate binomial probabilities. Also we have to take care the continuity corrections. If we have probability of this type, then this will be approximated by probability that x is less than or equal to x plus 0.5. And if we have probability that capital X is greater than or equal to small x, then this will be approximated by probability that capital X is greater than or equal to x minus 0.5. So with this in mind, we move to the second example. Example number 2. Suppose only 75% of all drivers in a certain state regularly wear a seat belt. A random sample of 500 drivers is selected. What is the probability that between 360 and 400 inclusive of the drivers in the sample regularly wear a seat belt? Fewer than 400 of those in the sample regularly wear a seat belt. So here the random variable under consideration is the number of drivers who regularly wear a seat belt among n equal to 500 drivers, and it is given that probability that drivers regularly wear a seat belt is 75%, that is 0.75, and we have sample of 500 drivers. And if we consider success as the event that drivers regularly wear a seat belt, then it is given that probability of success is 0.75. So here given random variable is a binomial random variable with n equal to 500 and probability of success equal to 0.75. So we define capital X to be equal to the number of drivers who regularly wear a seat belt among n equal to 500 drivers, that is given sample. If success is the event that driver wears a seat belt regularly, then it is given that probability of success is 75%, that is 0.75. So clearly X is a binomial random variable with parameters n equal to 500 and p equal to 0.75, and we are asked to find the probability that between 360 and 400 inclusively, that is we have to take less than or equal to and greater than or equal to sign. So we have to find this probability, and probability that fewer than 400 regularly wear a seat belt. Fewer than means we have to find that probability that number of drivers who wear seat belt, the number of drivers who wear seat belt regularly is less than 400. So we have to calculate these two probabilities. So we also go for normal approximation. Here we check two conditions. We first check whether n into p is greater than 5. So here n is 500, p is 0.75. So n into p is 375, which is greater than 5. And n into 1 minus p is 500, p is 1 minus 0.75. So this we obtain 125, which is greater than 5. So n into p is greater than 5 as well as n into 1 minus p is greater than 5. Therefore we can approximate given binomial random variable with normal random variable with parameters mu equal to n into p, which is 375, and standard deviation sigma equal to square root of n into p into 1 minus p, which is after simplification 9.68. So first we find out probability that capital X lies between 360 and 400. So as we discussed in the previous example, for less than or equal to type we have to add 0.5, and for capital X greater than or equal to 360 we have to subtract 0.5. So this discrete probability is converted in terms of continuous normal probability. So this is probability that 359.5 is less than or equal to X is less than or equal to 400.5. Then we standardize by taking X minus mu over sigma. So we subtract mu from each of these three and we divide by sigma. Then we substitute values of mu and sigma. Mu is 375, sigma is 9.68, and this is replaced by standard normal random variable z. And after simplification, we have probability that minus 1.60 less than or equal to z less than or equal to 2.63. And this is nothing but probability that z is less than or equal to 2.63 minus probability that z is less than or equal to minus 1.60. Now we use the normal probability table. First we find this probability. So we have to look for 2.63. In the table we search for 2.63. So under Z we have to search for 2. Under this column we search for 2.6. So here we have 2.6 and we have to go up to 3. 2.63 means we have to go up to 0.03. So this is corresponding to 0.00, this is for 0.01, 0.02 and this for 0.03, 0.9957. So we substitute here 0.9957 and then we look for minus 1.60. So we search for minus 1.6. So this is minus 1.6 and this corresponding to 0. So minus 1.6, here we have minus 1.6 and this corresponds to minus 1, this corresponds to 0. So minus 1.6.0 minus 1.60 is giving this probability 0.0548. So we substitute 0.0548 and the difference is 0.9409. So the probability that between 360 and 400 of the drivers regularly wear a seat belt is 0.999409. Second part is probability that fewer than 400 drivers regularly wear a seat belt. That means we have to find this probability that capital X is less than 400. But capital X is a binomial random variable, so it is discrete random variable. So probability that capital X is less than 400 means these are the possible values of X: 399, 398, 397 and so on. So X can take only discrete values. So probability that X is less than 400 can be rewritten as probability that X is less than or equal to 399. So this probability is converted in terms of this probability. So we know that if we have this type of less than or equal to probability, we have to add 0.5 to the X value. So here we have to add 0.5 to 399. So that is probability that capital X is less than or equal to 399.5. Now we standardize this probability. So probability that capital X is less than or equal to 399.5 equal to probability that X minus mu over sigma is less than or equal to 399.5 minus mu over sigma. Then we put values of mu and sigma and this is Z. So we obtain this probability is nothing but probability that Z is less than or equal to 2.53. So we search in the table for 2.53. So we have to go for 2.5. So here we have 2.5 and we have to go up to 3. So this is for 0, this is for 1, 2 and 3. So the required probability is 0.9943. So that we substitute here. So it is easy to approximate binomial distribution using normal distribution if we have this type of conditions satisfied and we have to use appropriate continuity corrections. So I stop here. I hope you like this lecture. Thank you very much.